for a couple of examples on geometric sequences, let's start with the one that we used when we defined a geometric sequence. And so here was the example that we used when we defined a geometric sequence, and we found that the common ratio was -1/3, -1/3. So if that's our common ratio, then we know from geometric sequences, from our proof right here, that if that ratio is between -1 and 1, which -1/3 falls in that ratio, that the limit goes to 0, which means that this must converge to 0. So we can say here that the limit as n approaches infinity of 5 times -1/3 to the nth, we know that this ratio right here must, as we approach infinity, that ratio, as we multiply -1/3 times itself, it's going to oscillate between a positive and a negative, but it's definitely going to be approaching 0. Therefore, this equals 0, and we have convergence. This converges to 0. Now, the other definitions that we went through on that first video about geometric sequences was monotone and bounded. So when we talk here about a monotonically bounded sequence, again, remember, bounded means that it's going to have a floor or ceiling, an upper or a lower bound, and monotone means that it approaches something, it is always increasing or always decreasing. So if we have a monotonically bounded sequence, that means that it's always going to increase or always decrease towards its bound. So just to add a little bit of language to this example here, if we've got this convergence to 0, if we're going to say, does this guy converge, we would say in this case, how does it converge? Well, it is not a monotone sequence. This guy is not always increasing or always decreasing. In fact, it's oscillating. We can see that in the expansion of the terms. And so this converges to 0, but it does so in a way that oscillates. So it converges to 0 through, we can add a little bit of language here, through oscillation. So this is not doing so in a monotone way. This is not always increasing or always decreasing. It's oscillating. It's going back and forth across the x-axis if we were to graph these terms, and it is converging to 0, but through oscillation. All right, let's do one more example, and then we can save a couple of these and do them during the class sessions. So here's a few examples. I'm going to go ahead and grab the one that's highlighted there, the sequence that is defined as 3 to the -n plus 1, e to the n plus 2 from 1 to infinity. So let's take a look at that example and talk about what happens to that guy. So if we had the example 3 to the -n plus 1 times e to the n plus 2 from n equals 1 to infinity. And let's talk about what happens here. So the a sub nth term, so if we're thinking about what this term looks like, I see those powers with the n's and with the constants and the exponents. And so I'm thinking, let's just play around a little bit with this and see if I can get it to look a little more like something that I can either take the limit of, or maybe it looks geometric. Let's take a look. So first of all, with that 3 to the -n plus 1, let's drop that into the denominator, n minus 1 on the exponent, and then continue to play around, and I can say, well, that's just e squared times e to the n, and 3 to the -1st times 3 to the n, if I just break up the actual exponents here. And then continuing to simplify just a smidge more, and I could say, well, that's the same as 3e squared times the ratio e over 3 to the nth. And so if we take a look at that, that is clearly geometric. That's clearly a geometric sequence. Notice here that this guy is actually always greater than or equal to 0. It's actually not even ever equal to 0. We could say that this is just greater than 0, which tells me that it's actually, just one other language definition here. This is actually a bounded below. It has a lower bound. Another way to say that is a lower bound. So this definitely has a lower bound. It is bounded below, has a lower bound, this sequence. And it's geometric, and the ratio is e over 3. But remember that e, 2.718, this has got to be less than 1. E divided by 3 is less than 1, which means that this must converge, because we can show here that the limit as n approaches infinity, and it was a little harder to show before we did the algebraic simplification, but the limit of the terms as n approaches infinity of 3e squared, that's just a constant, times e over 3 to the n. Well, since that ratio is less than 1, we know that this piece has to go to 0, which means this limit equals 0, and this guy converges to 0. And if we take a look at this sequence, the sequence is being multiplied, each term is being multiplied by a ratio that is less than 1, which means that this guy is actually always decreasing. So we could say that this actually converges to 0 in a monotone, always decreasing, to be specific, in a monotone way. Monotone meaning that it is always decreasing or always increasing. This particular sequence is going to be always decreasing. Each term gets multiplied by a ratio that is smaller than 1, which decreases it from the previous term, and we know that it converges to 0, so it decreases in a monotone way. It is also bounded, so we've got a lower bound and decreasing in a monotone way. So that's just two little examples where we talk about that language, one that oscillated and one that converged in a way that was actually monotone.